Hello, student. So this is our second lab on microwave engineering. Okay. So here we are going to design a branch line coupler in HFS. Okay, HFSS. Okay. So you have already given the lab sheet. Okay. I think it is already have been uploaded to the LMS. Okay. So here you have to design a branch line coupler and you have to calculate the important parameters related with the design. And here you are given the data. Okay, so the designing parameters related with the coupler is based on your last digit of your registration number. Okay, so you will have to do a different unique design as this as a lab activity. Okay, so here you are also given the important equation. Okay, and some designing parameters, mainly dimension of the coupler should be calculated using TX line tool. Okay, so this tool can be easily downloaded from the Google. Okay, so I hope you have the tool just now with your laptop. Okay, and you can proceed the designing. Okay, so you have to design the branch line coupler, then you have to simulate it in HFSS. Okay, so that is your lab activity. Okay, so as a demonstration, I will be designing a branch line coupler. Okay, I will be designing a branch line coupler. So 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 here you are given the designing parameters in the lab sheet. Okay, so these are your designing parameters. Okay, so I will so these are the actually these two, I think these two are the main designing parameters of branch line coupler: coupling factor and design frequency. Okay, so I will be using coupling factor. I will be getting a coupling factor as 6 dB and design frequency for 3 gigahertz. Okay, so so I'm going to design a branch line coupler with 60 dB coupling factor. Okay, coupling factor, and the designing frequency is 3 gigahertz. That means BLC with 6 dBm coupling factor for 3 gigahertz frequency. Okay, 3 gigahertz frequency, and the transmission line. Okay, transmission line impedance, transmission line characteristic impedance will be normally denoted as Z0, will be 50 ohm. Okay, so this is matched to 50 ohm line. Okay, this is matched to 50 ohm line. So all the designing are based on 50 ohm 50 ohm characteristic impedance, transmission line with 50 ohm characteristic impedance. Okay, impedance. So all these branch line couplers are matched to 50 ohm transmission line. Okay, it is given here. Okay, so I think you know about branch line couplers. Okay, you may have learned them in your lecture. lectures, so in your theoretical classes. Okay, so you can see that this is a 4-port network. Okay, so we have this is the input port. Okay, and this will be our output port, and this is the coupling port, and this will be the isolation port. Okay, so there are 4 port. Okay, there are 4 port. So this is a 4-port network. Okay, so this is a 4-port network. Sorry, this is a 4-port network. Okay, network. Okay, for 4-port network, we have 16 S parameters, 16 number of X parameters. Okay, number of S parameters are 16. Okay, so I think you have already know what is S parameters and how we can measure them. Okay, so in our first lab also we are we supposed to do the measurement, this S parameter measurement physically using the network analyzer. Okay, so here also we are going to measure this parameter using HFSS. Okay, so that is our task. Actually, we have to design the BLC, the branch line coupler first. Okay, then we have to simulate and we have to observe the S parameters. Then based on S parameters, we conclude our branch line coupler. That is our task. Okay, that is your task in this lab activity. Okay. Okay, so this is a 4-port network. Okay, so I think you have idea about this branch line coupler. Okay, so if this is the input port, if we send some power through this, okay, through this, it should be going in this way. Okay, and it should be not going to this way. Okay, so this path should be blocked. Okay, this is the isolation path, isolation port. Okay, so it is ideally the path, the coupling, there is no isolation, there is no power at the isolated port, but practically we have some power through this also. We have some very small power through this also. Okay, so anyway, to block the signal going through this branch, okay, you can see that we have to make this strip. Okay, make this strip, so these are copper strip actually. So this copper strip should be high impedance, high impedance. Okay, high impedance than this one. Okay, so this will be our low impedance section. Okay, so this will be our low impedance section. So this is high impedance section. Okay, and this also a high impedance section, and this one are low impedance section. Okay, so I take ZA as low impedance. Okay, so ZA is the low impedance, and ZB is the high impedance. Okay, high impedance. Okay, so we are going to design this branch line coupler in a substrate. Okay, in a substrate. So what are substrate? Okay, so I think if you have come to the laboratory one, okay, uh, you would be able to see them. Okay, you would be able to see them and observe them. Okay, so anyway, I think you have idea about this substrate. Okay, so there are many substrate available. Okay, so here this type of substrate are available in the market. Okay, so different designing, you are given different substrate. Okay, so these are the substrate these are the substrate property, and we have to use this property also to do our calculation, to do our design. Okay. So that informations are also given. Okay. So so for my designing, I will be selecting this Dielectric NX 9320 substrate. Okay. So I take this substrate for my design. Okay. This one. Okay. So this will be my material. Okay. So I will be using this one. Okay. So this is already we can find this material in the market. Okay. So this is actually a copper plate. Okay. So if I give you a general introduction about this Dielectric, the substrate board, these are available as board. Okay. These are available as board sheet. Okay. So it is like this. Okay. We have a very thin copper layer. Okay. Very thin copper layer. So this will be a copper layer. Okay. So this will be a copper layer. This is very thin. Okay. This is very thin. Okay. This is very thin. It is about 18 micrometer. Okay. So this is very thin thin copper plate, copper sheet. Okay. So when we are doing actually this thickness also affect to our this thickness also impact to our design, but we won't consider them because this is very low thickness and it will not impact much on our design. Okay. And also we have another dielectric material like this. Okay. On top of the copper plate, we have another dielectric material. Okay. This is a dielectric material. Okay. This is a dielectric material. Okay. Okay. And different board has different material. Okay. Material. Actually, this Dielectric NX 9320 means we are using Dielectric material here. Okay. So this substrate are named after the material. Okay. Name after this dielectric material. Okay. So this material, so different material we are using. Okay. So different material has different properties. Okay. And also the height of this material, height of this dielectric layer also will be changed. Okay, let's take it as D. Okay, so there is a, so but this D is very important. Okay, for many calculation we have to use this thickness, dielectric thickness. Okay, so this is very important parameters. Okay, so this is D is the height of our dielectric. Okay, and after that we have another copper plate. Okay, very thin copper plate, around micron, around 18 micron range. Okay, so we have another copper plate, copper layer. Actually, this is copper layer or copper sheet. Okay, so this is our board. Actually, this is a sandwich board. Okay, so between two copper plates we have a dielectric material. Okay, so this is our board. Okay, so this board has different dimension. Okay, available in the market. Okay, so normally this Dielectric board is 55 millimeter by 55 millimeter square board. Okay. Okay. So this is the top view. Okay. So this is a copper plate actually. This is a copper plate. Okay. Then we have the dielectric layer like this. Okay. We have the dielectric layer like this. And again, we have the other copper plate. After that, after the dielectric material, we have other copper layer also. Okay. So this is the top view. Okay. So we are going to design our coupler in this board. Okay. In this board. So say that if we have make a transmission line, this if we say that we want to make a transmission line through this board, then we have to mark it in this board. Okay, so sometime we may have to calculate the width and length of the transmission line depend on our design. Okay, so anyway, let's say we have calculated those values, then we can mark here. So all there are copper available. Okay, so using a chemical or something, if you remove the copper here and here, okay, so we will have this this copper strip only. Okay, so actually this type of transmission line we call that strip line, micro strip. Okay, micro strip. So if I get the if I get the side view, okay, if I get the side view, it is like that. So here we have a copper plate. Okay, okay, and here we have the dielectric constant. Okay, here we have the dielectric constant. This is dielectric material. Okay, so this is dielectric material. Okay, and again we have our microstrip like this. Okay, like this. Okay, so this is actually a microstrip. Okay, this is a copper plate, and this one also a copper plate. Okay, so this is our transmission line. You already know that you have seen signal generators, oscilloscope, like that. Okay, so they are to send the signal, we are using transmission line. Those are normally coaxial cable. No, those are normally coaxial cable. Okay, so you can see that for a transmission line there should be two conductor. Okay, one is a ground and other is a live one. Okay, other one is a ground and other is a live one. So here this is the live part, plus side, and this strip we can consider as our ground port. Okay, so if you want to feed any signal to this transmission line, okay, if you have a signal generator, you can get the signal generator output. So here you have a ground port and ground conductor and the live conductor. Okay, so you should connect this live conductor to this and ground conductor to this ground plate. Okay, likewise you can feed the signal to this micro strip. Okay, so actually if you have come to the lab, you can get the experience on this, but unfortunately only one student was there. Okay, anyway, okay, so now, okay, so now you can see that, okay, you can see that we have to implement that is the normal practice way. Okay, that is the practical way, that is in normal practice. Okay, we have to implement the coupler in this sheet. Okay, so we will have this kind of uh, coupler like this, okay, like this, okay, like this, okay. So you can see that if you consider this section, those are microstrip, so all these sections are microstrip. So here you can find these are transmission section, okay, so these are transmission line section, okay, uh, which we are used to feed the signal to this branch line coupler, and branch line coupler is start. This is the beginning point of the branch line coupler, and this is the end point, okay. So this will be the branch line coupler, this will be the branch line coupler, okay. So these are transmission line. So there are four transmission line for four port, no, there are four transmission line, four lines for four port, okay. And we have this low impedance section, okay. This is inside the branch line coupler, this is inside the coupler. So we have this high impedance section, okay, and this section also high impedance, okay. And we have low impedance section here, okay. So and also we have a low impedance section, okay, low impedance section. Altogether, there are 1, 2, 3, 4 transmission line section, TX line section, okay, and 1, 2 low impedance line section, 2 low impedance line section, okay, and 2 high impedance line section, okay. So there are altogether 8 sections, okay, mainly 8 section, 8 section available related with this coupler, okay. So all these sections are nothing but they are microstrip, okay, they are microstrip, okay? So that is the understanding you should get, okay. So all these sections are microstrip, okay. So all the calculation are based on microstrip theory, okay. Okay, so we will see, okay. So now I think now I think you have a general idea about this VLC coupler, okay. Then we will move to our design, okay. So as I told you that our designing will our VLC is a 60 dB coupling factor. Our VLC has 60 dB coupling factor, okay, coupling factor. And also we have our design frequency is 3 gigahertz, okay. So these are the basic two parameters, designing parameters, okay. So what is coupling factor actually? Coupling factor means, okay, this is the input this is the input power, okay. If this is the input power, actually input voltage, okay. If this is the input voltage, let's say that is A1, okay. A1 is the input voltage. So here I input A1 voltage here, okay. And if I get the coupled output, let's say it is B3, this is a 3 port, okay, B3, okay. So coupling factor is, okay, coupling factor is so these are voltage, okay. So normally coupling factors are measured based on power, okay. So we have to square the voltage to get the power, you know about the sinusoidal signal, okay, power content of a sinusoidal signal, okay. So this is normally we prefer to prefer to uh, say this uh, in decimal range, okay, in decibel form. So it will be minus 10 log, okay. So this the coupling power. So that means this is a voltage and you have to get the square, okay, coupling power, and you have to get the input power square, okay. So you will get minus 20 log B3 A1, okay. So this is the coupling factor. And what is this B3 A1? Okay, so here the input port is 1 and measured port is 3. Okay, so that is S31 parameters. No, so this is the input port and this is the measured port. Okay, so we have learned this in our lab 1. Okay, in our lab 1 I have explained this. Okay, in the physical lab session. Okay, so this is nothing but S31 parameter. Okay, so this is nothing but S31 parameters. Okay, so if you are given the coupling factor, that is 6 dB, okay, we can find the S parameter, magnitude of the S parameter actually. Okay, so here if I solve this, okay, I will get, okay, I will get this S31 as 0.5012. Okay, please check. Okay, so this is the S parameter. Okay, and this impedance, okay, this impedance, so what is this impedance? This is at A, is at B. So this is low impedance and the high impedance. Okay, those impedance are also based on, okay, are based on this parameter S31. Okay, so I have given it. Okay, so I have given it. So here I have given the coupling factor. Okay, then I have given how this how this the S31 parameter is related with the impedance. Okay, impedance. Okay, so using this equation, you can find the ZA and ZB. Okay, so I am not going to do the mathematical things here. Okay, it will take the time. Okay, I think it is very simple. You have to solve some equation. Okay, then you can calculate. Okay, then you can calculate this ZA and ZB. Okay, so I have already calculated them. So I get ZA as 43.3 and ZB as 86.4. This is ohm and this is ohm. Okay, so I have already calculated. Please calculate. So this for your design, this value will be changed because you have different design frequency and different coupling factor. So so this is a low impedance. Okay, so this is the low impedance and this will be the high impedance. So this will be changed for your design. Okay, so in my design I get this value. Okay, once I solve the equation. Okay. Okay, so now I have calculated the characteristic impedance of this transmission section, okay, or microstrip. Okay, so I have calculated this this one and this one. This are low impedance section, and this one and this one. This are high impedance section. I have already calculated. Okay, and what is the characteristic impedance for transmission line? It is given as 50 ohm. Okay, so already it is given as 50 ohm. So Z naught is 50 ohm. So you have, so this is given and you have to calculate these impedances. Okay, So this is the transmission line, feeder line. This is for feeder lines. Okay. Okay. So we have to find, okay, so based on these impedances, okay, based on these impedances, we have to find the width, okay, width and the length of this transmission line section, okay, related to microstrip. Okay, so for that, okay, so there are many equations in your textbook. You can find those equations related with the microstrip chapter. Okay, so I am not going to use the equation. These are very large equation. Okay, but using a calculator, simply you can calculate the value. You have to substitute the value to that equation, and you can find the necessary parameters. You can calculate the necessary parameters. Okay, so it is also very it is also not a big deal. Okay, you can simply do it. Okay, but here we are not going to use the equation. For that one we are going to use what is called tx line tool. Okay, so here we have a tx line, and it is we can calculate many related parameter with the with the microstrip. Okay, uh, many related parameter with many component. Okay, so you can see that microstrip, the strip line. Okay, so this is what is this waveguide? I can't remember the name. The polar waveguide or something. Okay, I can't remember the name. Okay, so these are coaxial, slot line. Okay, MS line, coupled strip line. So there are many components, microwave component. Okay, actually these are transmission line, microwave transmission line. Okay, these are microwave transmission line. Okay, so there are different transmission line available. So for different transmission line, we can calculate different parameters using this tx line tool. Okay, so here we are going to use microstrip because our design is based on microstrip. Okay, uh, so here you are given a microstrip also. Okay, so you can see this is the ground plate, copper plate, and this will be your dielectric material, and this will be your this will be the width of the microstrip. Okay, so this width mainly depend on the relative permittivity of this dielectric constant. Okay, this width. Okay, okay, so the width of the transmission line, okay, width of the transmission line mainly depend on the relative permittivity of the dielectric or this is called dielectric constant. Okay, this is also called dielectric constant. Okay, relative permittivity, dielectric constant. Okay, relative permittivity of the material, dielectric material, and also the thickness of the dielectric material. Okay, so mainly width is depend on these two parameters. Okay, and and also based on characteristic impedance. Okay, so this width of the transmission line, microstrip line, will be based on the relativity permittivity and thickness of the dielectric material, and also based on the characteristic impedance. Okay, so the equations are available for that. Okay, to calculate the width and d and z naught, you have equation. Okay, so using equation you can calculate, but here I am going to use the tx line tool. Okay, So let's calculate. So this this these material properties are also given. Okay, so you have to use different substrate for your design. For different all the substrate, you are given the required property of the material property. Okay, so this is the material. Okay, and so here for we are using this Neltec NX9320 material. Okay, so relative permittivity is 3.2, and another parameters is the allostagnant, and dielectric thickness is 0.762. Okay, so for our design, okay, so we are using this Neltec 93X20 board. Okay, so here dielectric thickness is 0.6762 millimeter. Okay, and the dielectric constant is 0.2. Relative permittivity is 3.2. Okay, and okay, so these are the required value. Okay, and now you can use the TX line to calculate the width. Okay, so first we measure the width of the transmission line. Okay, so width of this transmission line. Okay, so what is the dielectric constant? It is 3.3. Okay, so loss stagnant also given. I have put the loss stagnant also. Okay, so I will choose copper. I think if you are using this copper or silver, it will not impact to the width or height. Okay, so I just select. Okay, and impedance is very important. This parameter is very important, so it will be a 50 ohm. Okay, and also I put the frequency also here, 3 gigahertz. Okay, 3 gigahertz. Okay, sorry, 3 here gigahertz. Okay, and other things no need to change. Okay, and we have to put the height. So these are the physical characteristic of the microstrip. So I have to give the height. Height means this dielectric material height. So that is 0 point thickness. No, that is the thickness of the dielectric material. So it is 0.762 millimeter. 0.762 millimeter. And also we have the copper thickness that is normally in the market. It is around 18 micrometer. So I have put that one also. Okay, so actually very importantly, this one and impedance and height, these three parameters are very important. Okay, others will affect but not much. Okay, maybe this frequency is affect to the width, but it is not too much. It is not, we can neglect those impact. Okay, we can neglect those impacts. Okay, so but these are very important, so you have to insert correct value here, the dielectric constant, impedance, and height of the dielectric material. Okay, so it is around 1.81 millimeter. Okay, so I will get it as 1.8 millimeter. Okay, so I have calculated the width of this transmission line, so that is 1.8. Okay, so I will use another sorry. Okay, I will use another diagram. Okay, see to mark the dimension. Okay, because these dimensions are very important. These dimensions are very important when we are doing the design. Okay, so here okay, so now we have calculated this width. Okay, the width, this width. Okay, So that is 1.8 millimeter. Okay. So this width is 1.8 millimeter. Okay. So all transmission line are 50 ohm. Okay. So all transmission line have same thickness, same width. Okay. That is 1.8 millimeter. Okay. Then so let's find the width of this low impedance section. Okay, so there are two low impedance sections. Okay, let's find the width of these two low impedance sections. Okay, so you can remember the low impedance that is 43.3 43.3. Okay, so I put impedance 43.3. Okay, then I calculate. So it is around 2.26. Okay, that is 2.3. Okay. So if I this calculate I have calculated this one, it is 2.3 meter. Okay, 2.3 meter, and this one also 2.3 meter, the width. Okay, and let's find the high impedance line section width. That means this width. Okay, so you can use the transmission line, and you have to impedance the high impedance. Okay, you have to insert the high impedance. What is that? 86.3 or something. 86.4. 86.4. Okay, so I have calculated. So it is about 0.64. Okay, so that is 0.64. So this is 0.64. Okay, so we have calculated the width. Now we have to calculate the length of this transmission line. Okay, length of this transmission line. Okay, so for a branch line coupler, this length is very important. Okay, so we have basically three lengths. Okay, so high impedance line length and low impedance line length. Okay, and also the transmission line length. Okay, so you know that. Okay, so this is 90-degree BLC. Okay, branch line coupler. That means when a signal is if a signal is insert here, and if it is going through this coupler to this end. Okay, this end, there should be 5/2 phase shift. Okay, there should be 5/2 phase shift. Okay, so we know that for lambda or yeah, for lambda we have 2/5 phase shift. Okay, so you know that these are sinusoidal signal like this. Okay, so if you consider this lambda, okay, so here the phase shift is 2/5. Okay, so for lambda there is a 2/5 phase shift. Okay, due to delay. This happened due to delay, actually propagation delay. Okay, so for 1 radian, we have lambda to 5. Okay, lambda to 5, and for 5/2 phase shift we should have lambda by 4 length. Okay, so this high impedance section and low impedance section should be lambda by 4 length. Okay, so this length should be lambda by 4. Now the problem is, what is the lambda? So what is the lambda? Okay, so we know that V equal F lambda. So we know the V 3.10 to the power 8, and we have F. So that is our design frequency, 3 gigahertz, and we can calculate the lambda here. Okay, but keep remember that this is the free space lambda. Okay, this is the free space lambda. But these are microstrip. Okay, so this lambda will be changed on microstrip. Actually, this lambda also depend on this lambda. Okay, let's say that it is, we called as, I can remember, it is effective lambda. Okay, lambda g is based on lambda divided by square root epsilon effective. Okay, epsilon effective. Okay, so this epsilon effective is not the dielectric constant. Okay, so so dielect so this epsilon effective is uh, depend on the dielectric constant, that is epsilon r. Okay, epsilon r, and also this epsilon effective will based on width and the height of the dielectric constant. Okay, so epsilon, this epsilon effective will be depend on these three parameters: epsilon r, width of the microstrip, and the thickness of the dielectric constant. Okay, so you know that these two again depend on the characteristic impedance Z. Okay, so you can see that this epsilon effect will be based on mainly epsilon r and characteristic impedance. Okay, so this lambda g will be based on these parameters and this lambda. So then the length also will be depend on these parameters. Okay, so you can see that these have different characteristic, no, different characteristic impedance. Okay, so this have 43.3 ohm, and this high impedance section has 86.4 ohm. Okay, so it has different impedance, different characteristic impedance, but dielectric uh, dielectric uh, dielectric constant and the 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 thickness of the dielectric material is same. Okay, but it has different uh, impedance, so this length will be different. So for so if I tell the summary, for high impedance section will have one length. Okay, one length. Okay, and the low impedance section has another length. Okay, so this is the low impedance length, section length, and this will be the high impedance section length. Okay, so we can calculate these two length also using the transmission line. Okay, sorry, TX line tool. Okay, so here this is the high impedance. Okay, so this is the high impedance. Okay, and I forgot to tell you that. Okay, this lambda g, so you can see that this lambda is mainly depend on frequency. Okay, okay, because we equal f lambda. Okay, so this length also will depend on uh, the frequency. So you have to put the frequency here. That is very important. Okay, so when you are calculating the length, okay, so the dielectric constant is very important, and frequency you should put, that is very important. Okay, and impedance is also very important, and you have to put the electric length. Okay, that is actually phase shift. This is the phase shift. Okay, the electric length is, as I can remember, it is defined as beta L, where beta is the phase constant. Okay, so this beta L is the electric length, and also we can denote the electrical length in radians. Okay, so this electrical length is the phase shift. Okay, so we are expecting 5/2, that means 90 phase shift. So here you have to put 90. Okay, so these parameters are very important when you are finding the length, the dielectric constant, impedance, frequency, and electrical length. Others are not much important. Okay. Okay. So if I calculate, okay, so I will get 16.2. Okay, 16.2. That is our high impedance section, no, length for high impedance section. Okay, so we have calculated. Okay, we have calculated this one and this length. Okay, so if I put line here. Okay, okay, so this is the middle line of this couplers. Okay, so this point to this point length will be 16.2 millimeter, correct? So that will be 16.4. In the same way, you can find the length, this one and this one, this length also. That will be, so here, that is our high impedance section, no? That is 43.3. Okay. So that will be 15.4. Okay. So that will be 15.4. Okay. So this value will be 15.4. Sorry, this value from here to here, this value will be 15.4 millimeter. Okay. So these are the important parameters. Okay. And what about this transmission length? Okay. So we are not expecting any specific phase shift. Okay. So you can get appropriate the practical value for this transmission line. Okay. So I will take it as 10 millimeter. Okay. So these are the parameters. Okay. So let me again mark the parameters clearly. Okay, because that is very important for our design. Okay, so this is the branch line coupler. Okay, and here we have put like this. Okay, and this to this we get 16.2 millimeter this length, and I get like this. Okay, I get here 15.4 millimeter. Okay, okay, and this width is 2.4, 2.3. Okay, that means this half is 1.15. I will take as 1.2. Okay, and this half also 1.15. I will take as 1.2. Actually, I take this 1.2 because previously I take this as 2.4. Okay, so I have already calculated some coordinate. Okay, so I will if I get this as 1.15, all coordinates are we have to change the all coordinates. Okay, so it will take some time to calculate the coordinates, so I take it as 1/2. Okay, and here this length will be, the total length will be 0.64, and this length will be 0.32, and this half length also will be 0.32. Okay, and we have the transmission line that is from here to here. Okay, here to here we have 10 millimeter, and here also we have 10 millimeter. Okay, so now we have to design this on a board. Okay, so our board is about, I already told that it is around, normally in market we available 55 millimeter to 55 millimeter board. Okay, so if I calculate the length from here to here, okay, from here to here, what is the length? That is 10 millimeter plus 0.32, 0.32. Then here to here, it is 15.4 plus again 0.32. Okay, so I have already calculated this. Okay, the value is, what is the value 16.04. Okay, so this value is 16.04. Please use the calculator and add. It is 16.04. Okay, so if I so this is the length of the substrate, required substrate. So we have 55 millimeter. Okay, so you can get the tool and you can cut the appropriate size and you can use that size for this coupler only. Okay, so I will get 16.0 millimeter length substrate plate. Okay, you can cut this and you can make it as appropriate. Okay, then what is the width of my substrate? Okay, the total substrate. So I take 5 millimeter from here. Okay, 5 millimeter from here and also 5 millimeter from here. So what is the so this will be 5 millimeter, and this is already we have calculated, and this will be, what is this length? It is 5 millimeter plus 5 millimeter plus 5 millimeter plus 1.2 plus 16.2 plus another 1.2 plus this 5, another 5. Okay, so it is 5 plus 1.2 plus 16.2 plus 1.2 plus 5. Okay, so you have, if you add all these together, I already have added using a calculator. I get 20, I got 28.6 millimeter. Okay, so this is the width. Okay, so the required width also you can cut using a cutting tool. Okay, so I get only this section for my design. Okay, so it is 16.04 long and 28.6 millimeter wide. Okay, so I take this plate. Okay, so you know that if we take this plate, it has a dielectric constant, dielectric material like this. Okay, and also after this dielectric material, there is another plate. There is another copper plate. Okay, so here also we have a copper plate, another copper plate. Okay, after the dielectric constant. So it is like that. We have a copper plate here, and then we have our dielectric constant, dielectric material. Then we have a copper plate here. Now we are going to do the design on this side, and this side will be a ground plane. Okay, so this side will be the ground plane. Okay, this side will be the ground plane. Okay, so I have already told that for designing, we no need to take the copper thickness into account. So we can say so we can imagine that the copper strip are only two-dimension device, two-dimension shape. Okay, rectangle shape, because no width, we are not going to get the thickness of the copper. Okay, but for this dielectric material, you have to get the given thickness. It is very important. Okay, so for this dielectric material, you have to draw a 3D rectangle. No, it should be like this. It is a box. Okay, you have to draw a box. Okay, and for the ground plane also, you can draw a rectangle. Okay, so likewise we can do the design in HFSS. Okay, so I will go to Okay, we are going to use HF. Sorry. This is okay. So I am going to use HFSS. Okay, so I open HFSS. Okay, so this ANSYS is the company, the the owner company of this software. Okay, so this also owned by Ansoft company also. Okay, so sometime you can see that this is as Ansoft HFSS. Don't confuse with that name. Okay, so anyway, this is a high frequency simulation tool. Okay, so this is very powerful tool in industry and for academic purpose also. We are using this simulator, okay, to simulate many device related with high frequency device such as antenna, filters, couplers, so on. Okay, so gradually we will see what are the facilities we have and how we can do a simulation in this software HFSS. Okay, so first of all you have to get the new project, this one, insert HFSS design. Okay, so here you have once you have design, you have insert the design, you will get this Cartesian space. Okay, so you can see that here we have to draw the object. Okay, so here we have to draw our ground plane, and we have to draw our dielectric material, then we have to draw our coupler. Okay, so basically three things we have to draw. Okay, so the length and the height, width, these are based on these coordinates, x and y coordinates. So we have to calculate the x and y coordinates in appropriate way. Okay, in appropriate way. Okay, we will see the so you can do it as you wish. Okay, you can select this x and y coordinate as you wish. Okay, uh, so we will see how to use them. Okay, so first I am going to write my ground plane. Okay, so therefore for that I use a rectangle. Okay, rectangle shape. Okay, so you can see that will delete this. Okay, so you can see that in this window we have different 2D these two-dimensional shapes. Okay, these are two-dimensional shape. Okay, and here you can see that we have three-dimensional shapes also. Okay, these are okay. So I take rectangle. Okay, then I write it here. Okay, so this is a rectangle. Okay, so this is a 2D 2D object, 2D shape. Okay, so you can see that if I right click here, so you can see once we add the shape here, it is appear in this area. Okay, it is appear in this area. So here we can change the properties. Okay, physical properties and other properties. Okay, using this menu. Okay, so if I double click on this rectangle one, you can see that I can change the color, I can change the name also. Okay, and also I can change the transparency. Okay, so here this is the copper plate, so I will use the copper the color appropriate for copper. So I will use here we can use yellow color for copper. Okay, so now you can see that it is in yellow color. Okay, now if I double click this create rectangle. Okay, so here I can get the coordinates related with the rectangle. So here I can change the position and I can change the dimension of this rectangle. Okay, so So, so to get the idea, I will put some, so position I will make as 0, 0, 0. So let's say x-axis length is 1 millimeter and y-axis length is 1 millimeter. Okay, so you will get this kind of rectangle. Okay, so this is the 0, 0, 0. So this is our starting point position of this rectangle. Okay, so it is here. Okay, and along the x-axis you have 1 millimeter. Along the y-axis also you have 1 millimeter. Okay, so in this way you can change the position and the length of the rectangle. Okay, so before that, so normal way, we know that normal way. Okay, so you can do any you can do the design in any orientation. So normally I familiar with this y is this axis and x is this vertical axis and z is like this. So this orientation I normally use. Okay, I'm familiar with this orientation. So I think if I change the orientation, it will be easy. Okay, it is not compulsory. You can do the designing as like this. Okay, so anyway, for me, I think it is easy to change the orientation as the usual form. So these tools we can use to change the orientation. Okay, so if I click here, so you can see that I can rotate this. Okay, so how I rotate? So y is in vertical axis, so in like this, no? Okay, so this is our usual orientation. Okay, so this one I can get this here. Okay, so I will use this like this. Okay, okay, so now I have a rectangle. So the rectangle position is start here at 0, 0, 0. So it has a width from z x direction, x plus direction 1 millimeter and y plus direction 1 millimeter. So what are the value we need here to here and here? Okay, okay, so I will use, okay, so I will start like this. Okay, so this is my x-axis. Okay, I will, so this is my y-axis, sorry. Okay, so this will be my y-axis and this will be my x-axis. Okay, and this is the plate. This is the plate. Okay, we want to create. Okay, so here for x-axis, it should be this total length from here to here, that is 16.04. Okay, that is 16.04. Correct? Sorry, I think this is 20. So here also I have to add the 10 also. No? This is 10, 0 0.32, 15.4, 0 0.10. Then this 10 also I have to add. Okay, so I have to add the 10 here also. So this will be 26.04. Okay, okay, correct. From here to here, I have to add 110 millimeter. Then I have to add 0.32 plus. I have to add this length 15.4 plus another 0.32 plus 10. Okay, so from here to here, I get 28.6 millimeters. Okay, 28, sorry, 26.4, 26.4, this 26.04 millimeter. Okay, this is the 28.6. Okay, so this is 26.04 millimeter, the length from here to here. Okay, correct. Okay, then I change. Okay, then here I keep the position 0, 0, 0. Okay, then I change x-axis. I change the x-axis length for 26.04, okay, and y-axis 28.6, no, okay. Okay, so I have, okay, so this is our rectangle, okay. So we have designed the we have write the ground plane, we have draw the ground plane, okay. Now we will draw so I think this is 36.04, no? This is 10.15.4, that means 25 plus 10, that means 25 plus 10 means wait 10.0.32 plus 15.4 plus 0.32 plus 10. Sorry, it is 36.34. Okay, so this length will be 36.04. Okay, it is a minor mistake. Okay, so this is 36.04. Okay, let's calculate this value also. It is 5 plus 1.2 plus 16.2 plus another 1.2 plus 5. Okay, so it is 28.6. Okay, it is correct. Okay, so this length will be 36.04 and this point will be 28.6. Okay, so I have so this x-axis should be 36.4. Okay, I'm sorry, it should be 36.04 and the y-axis should be 28.6. Okay. Okay, so this is my ground plane. Okay, so on top of this ground plane I have a box. Okay, that box is the dielectric material, no? So I can so I can make a I can draw a box here. Okay, so here I will make a box. Okay, like this. Okay, like this. Okay, so this box, so this is a box. Okay, so you can see that the box should be top of the ground plane and it the thickness should be 0.74. Okay, the thickness should be 0.762. Sorry, 0.762. This one. Okay, that is the thickness of dielectric material. So we have drawn the dielectric material. Okay, so that is the thickness of dielectric material. Okay, so so if I write here, so I will change the color to red. Okay, so that is our dielectric material. Okay, the color. Okay, then importantly we have to change the coordinate. Okay, so the position is 0, 0, 0. The x-axis also 30.36.04, that is correct, and y-axis will be 28.6. Okay, when you are drawing the box, if you have different value, please change it to this value. Okay, then it will be nicely fit to the ground plane. Okay, so I have so normally when I draw the box, it is already fixed. Okay, So it is 36.04, 28.00. So this is a so this is a 3-dimension. Okay. So it has X value and Y value, and as well as it has a Z value. So you can see that when we are drawing the rectangle only, we doesn't have to give a Z value, no, because it is a 2D value. But here we have to give the thickness. So what is this thickness? It should be 0.762. Okay, that is millimeter. 0.762, correct? 0.762. Yeah. Okay. So we have the ground plane, and now then we have the dielectric material. Okay. Now we have to assign the material. Okay. For that one, here I right click on this box. Okay. Then here you have the material. Now material is vacuum. Okay. But I have to change it to the, so our material is what? It is Dielectric. So normally these materials are given. Okay. Dielectric. It is Dielectric in X 9320. No, this one. So this is our material. Okay. So these materials are given sometime. Okay. Normally all materials are given. So you can see that the relative permittivity is 3.2. Okay. You can you remember it is 3.2. So I will put that, I will assign that material to this one. Okay, so it apply. Okay, so we have assigned the material. Okay, now it is so now we have the material name here. Okay, but when we are going to assign the material for this one, okay, so these are 2D shape. These are sheet actually. Okay, so here you can see that it is on the sheet. Okay, so these are on the solid. Okay, so solid component we can assign the material directly, but for sheet we can't assign the material. You can see that if we right click here, so here no material option. Okay, so here no material option, so we can't change the material here, but you can see that this is a copper. No, that is a copper. The copper is a conductor. Okay, so so we can, okay, for this type of the 2D sheet, we can assign the boundary. Okay, boundary as a perfect electric conductor. This means perfect electric conductor. So I can assign this this rectangle shape, okay, 2D shape as perfect E. Okay, so it is also infinite ground plane. No, it is a ground plane. No, so I choose like this. Okay, now I have assigned the the boundary. I have assigned a boundary as a perfect electric conductor. So the copper is also perfect electric conductor. So it will act as a copper plate. Okay. So when we are adding boundaries in this project manager window, also we can see. Okay. So when we click it, so you can see that we have assigned this as perfect E. Okay. So you can, if you can see that you have the ground plane, this is the ground plane, and this is the this is the dielectric material, and also top of the dielectric material you should have another copper plate. Okay, so I get another rectangle. Okay, I draw it here. Okay, draw it here. So we have rectangle 2. Okay, now when we assign the boundary, it is here it is mentioned. No, here we can note down it. We can see it as perfect E. okay, but these rectangles is still no, we didn't assign anything for this rectangle, so it is in unassigned form. Okay, so this rectangle also I can change the color, okay, because it is copper. Okay, and I have to change the coordinate also. Okay, so it should be, yeah, okay, so you can say that the position is 0.0.0.6762. That means this the later drawn rectangle is on on top of the material. So that is why position is 0.762. If I put this to 0, okay, if I put this to 0, you can see that it is going to the 0th value. So Z is 0. So it is not top of the dielectric material. Okay, so we have to get it top of the dielectric material. So we have to put 762. Okay, and it has also the so here it has also the same dimension. Okay, same dimension. Now if you look at this, okay, if you look at this, okay, so we have one copper plate that is for ground plane, and then we have the dielectric material, then we have the other copper plate. Okay, then we have other copper plate, correct? Okay, okay, so now our substrate is okay. We have a substrate for uh, we have a substrate in required dimension. Okay, now we have to remove the unnecessary copper. Okay, we have to remove this unnecessary copper from this line and this line. We have to make this coupler. Okay, so how we can remove the copper? Okay, so actually we can do it. There is a command. Okay, so here you can see that this comma, it is not highlighted at this moment. Okay, so you can see that this is subtract, unite. Okay, so there are many commands. Okay, we can use this subtract command to get rid of the unnecessary copper copper parts. Okay, so how can I do it? Okay, so I consider, okay, so now I have I will consider this as a one rectangle. Okay, I will consider, so you can get rid of this material any as you wish anyway. Okay, so for example, if you can calculate this value, okay, this value, you can draw a rectangle here. Okay, in the HFSS. Okay, here you can draw a rectangle with that dimension here. Okay, then you can subtract it from here to here, then that copper part will be cancelled. Okay, likewise you can get rid of other parts also. Okay, I am going to do it in this way. Okay, so in that way I have to remove this one, this part, and this part, then this part and this part also I have to remove. Okay, so I will do it like this. Okay, first I consider this as a rectangle. Okay, because these are dielectric. No, these are dielectric. So these are dielectric. Okay, so I only get this section rectangle. Okay, this section rectangle. Okay, so if I get only this section rectangle, I get this section only. Okay. So this part also will have a rectangle. Okay, not in this way. Okay, we have a rectangle shape because it is hard to remove this like this. Okay, so we will have first we will have this rectangle. Okay, so that means if we have this rectangle, that means these parts are not available. Okay, only we have this rectangle. So these are dielectric constant. Okay, so if I have this rectangle, okay, what is the length of this rectangle? It is you can see that it is 0.24 plus 15.4 plus again 0.24. So length of this section, okay, this section is 15.4 plus 0.23, this section plus this section 0.23. So if I add this together, okay, I will have 4 0 16.04, no, 16.04. So I will have 16.04 from here to here. Okay, and what is here to here? What is here to here? This length. What is this length? That is 1.2 plus 16.2, that is here to here, 16.2 plus another 1.2. So we will have 18.4, 18.6, no? So this line will have 18.6. Okay, so this is, we have 16.04 and this is 18.6. Okay, so this is 16.04, this line, and this part will be this direction from here to here, it will be 18.6. Okay, so I draw that rectangle. Okay, so you can see that this rectangle I have to remove, no, this section. So I am not going to remove it. I just make this dimension according to that rectangle. Okay, the required rectangle, that means according to this rectangle. Okay, according to this rectangle. So this is rectangle 2, no? Okay, so I make the dimension, I change the dimension. Okay, so we have to change the position. Okay, we have to change the position. Okay, so you can see that. Okay, so this we have to take this position, we have to calculate this coordinate. Okay, and we have to calculate this coordinate. Okay, so this coordinate, what is this coordinate? It is 10 millimeter, no, it is 10 millimeter because the transmission line. Okay, so this is 10 millimeter, and what is the here, it is 5 millimeter, no, we get 5 millimeter. So here to here, so it is x-axis is 10 millimeter, y-axis is 5 millimeter. Okay, so I put like that. Okay, so x-axis will be 10 millimeter. Okay, and y-axis should be 5 millimeter. Okay, and this y-axis should be 5 millimeter. Okay, then okay, so this x-axis, what is the x-axis length? Okay, what is the length? So this is the length, no, this is x direction length from here to here. Okay, so this is the x direction length, that is 16.04, and y direction length, that is from here to here, that is 18.6. 16.04, 18.6. Okay, so this is 16.04, and this is 18.6. Okay, so now when we apply it, you can see that that is shifted to here. So this will be 10 millimeter, this will be 10 millimeter, and this will be 5 millimeter. Okay, so we shift 5 millimeter here and we shift 10 millimeter here. So this length will be 16.04 and this will be 18.04. Okay, now I have to make the coupler. Okay, I have to make the coupler here. So to make the coupler, okay, I have to, so here now I have this copper history. Okay, so if I remove this copper, if I remove the copper in this area, okay, if I remove the copper in this area, if I remove this area, okay, I have only this line, no? This high impedance line I have, sorry, low impedance line I have, and we have this high impedance line, correct? Okay. So again, I write it here. Okay. So now we have drawn this rectangle. Okay. Now we have already drawn this rectangle. Okay. This rectangle we have drawn. Okay. Now what I am going to do? I am going to, I have only this line, no? This line I should have, this line I should have, this line I should have, this line I should have. So only, so required area is this. This we need, this area we need, and this area we need, and this area we need. So these are the required area. Okay. So to uh, to keep that area, to keep that section, I am going to remove this section. Okay, I'm going to remove this section. Okay, for that I have draw a rectangle on this plate. Okay, then I can subtract this one from here, this one from this rectangle. So let's say this is rectangle 2. Okay, I have draw another rectangle, it is rectangle 3. Then I subtract rectangle 3 from rectangle 2. Then I get only this history. Okay, correct. So we will do. So to subtract, what you have to do? You have to find this position. Okay, you have to this position. So this is the starting position of the rectangle. Then you can give the length. So the length should be this one and length should be this one. So what are the length? Those things you can calculate. Okay, so how to calculate? Okay, so you can see that here to here it is 15.4. Okay, and if you remove this part and this part, that means if you reduce 15.4 from 0.32 minus 0.32, that is the length of this inner rectangle. What is that? Okay, so you will get 6, 6. You will get another 3. So you will get here. So I use the calculator. 15.4 minus 0.32 minus 0.32. I will get 14.76. Okay, so here I get 14.76. Okay, so that is this length, no? This length from here to here, 14.76. Okay, 14.76. And what is this value? What is this value? Okay, what is this value? That is, so here so you can see that I will so you can see that from here to here, from here to here, this way, okay, you have 16.4 millimeter, 16.2. Okay, so if I remove, if I subtract this 1.2 part and this 1.2 part. That means if I remove 2.4 from this, okay, so 2.4 from this, I will get this value, no, from here to here. So what is that? That is 8, 15 minus 13.8 millimeter. Okay, so this section will be 13.8. Okay, so if I write it here, okay, if I write it here, okay, so you can see that this is 0.32 and this is 15.4. So I remove 15.4, 0.32 and this 0.32. Then from here to here, I get 14.76, and here from here to here I get 13.8. Okay, 13.8. Okay, so I will I will draw a rectangle here, another rectangle here. Okay, so I will draw another rectangle here with this position. Okay, so I think if I shift this one here and this one here, it will be easy. Okay, then so I will shift it. Okay, so I will shift this rectangle one. Okay, so here from here to here it is 10 millimeter. So I will shift that one also from 10 millimeter. Okay, so that means if I put the x-axis position here 10 millimeter, I think it is shifted minus 10 millimeter. Okay, minus 10 millimeter. Okay, so you can see that that copper plate, the bottom copper plate, ground plate is shifted to 10 millimeter here, and also I shift this box also 10 millimeter. Okay, so if I move this box also 10 millimeter to the minus side, that means minus 10 here position. Okay, position will be changed. That one also change. That one also shifted. Then I shift this one to exactly to y-axis. Then I think I can do the design somewhat easily. Okay, so that is rectangle 3. No, that is rectangle 2. Okay, so I am going to change. It is in 10 position. So if I put 0 here, okay, so that means if I put 0 here, that means it will shift here, no, to the y-axis and x-axis. Okay, now what is the value here? So you can remember that here the high impedance line is 0.64. Okay, 0.64. Okay, so x-axis I put 0.64, and if I put y-axis, okay, that is 2.4. No, the low impedance line is 2.4. Okay, so if I move this rectangle, so that is rectangle 3. Okay, if I move this rectangle, okay, position x-axis, it is 0.64, that is low impedance line width. Okay, and y-axis I move 2.4, that is y-axis, that is the high impedance width, high impedance line section width. Okay, and the position should be here, this position also should be 0.762, otherwise it is not top of the this plane. Okay, so that position should be there. And what is the x-axis value? Okay, x-axis value is 14.74. No, it is 14.67, sorry, 76. 14.76. Okay, this is x-axis and y-axis is 13.8. No, this is 13.8. This is 13.8. 13.8. Okay, so I put it 13.8. 13.8. Okay, so if I, so it is like this. Okay, but it is not like this. Yeah, so I have to add another 5 millimeter, no, because this is uh, so here we have moved this rectangle 5 millimeter from to the y-axis. Okay, so I have to change I have to add 5 millimeter to y range. That means it should be 7.4. Okay, 7.4. So this we have this two rectangle. Now I am going to subtract. So I click Control. I select this rectangle and I select this rectangle. Now you can see that subtract is highlighted. Then I can subtract. Okay. So you can see that now we have subtract. So you can see that we have prepare this high impedance section. So low impedance section, 2.4 millimeter width, and these are high impedance section. That is uh, 0.64. Okay, so we have almost complete our branch line coupler. Okay, so you can see that we have this way. Okay, this way. Okay, we have this low impedance section, and this is also low impedance section, and this high impedance section, and we have this high impedance section. Now we have to add this transmission line. Okay, so you have to calculate this point. Okay, you have to calculate this point. Okay, and also you have to calculate this point. Then you can add the add this transmission line as rectangles. Okay, add as rectangles to this design. Okay, so to do that you have to calculate this point. Okay, this point, let's take this point. Okay, that is match with this line. Okay, that is match with this line. Okay, so how to calculate this? Okay, so I think all required details are there now. So can you take some time and calculate this? Okay, I will calculate. Okay, but I think if you can do the calculation by yourself, it is okay. Okay, so so I think so I get one. Okay, so what you have to do is, okay, you have to, okay, so this is the branch line coupler. Okay, so you can see that now we have already completed these parts. Okay, we have already completed this section. Okay, these sections are already completed. Okay, these sections are already completed. Okay, now you have to add you have to add this transmission line. Okay, this transmission line. So there are 4 transmission line. Okay, so I am going to add them as a rectangle. To add the rectangle, okay, so I make this transmission line match with this line. Okay, match with this line. Okay, so what I have to do is I have to calculate this point. I have to calculate this point. Okay, so you have all required details. You have to add in and subtracting. Okay, so you have this length. Okay, and you have this These length, all the length, required lengths are available. So can you can you give a try to calculate this by yourself? I think when you are drawing, when you are going to do your design, I think first if you can mark all these coordinate, it will be easy for you to do the design. Okay, so can you take some time? Okay, can you take some time and do this? Okay, so here you have to do this. So what you have to do is you know this value and this value. Okay, so you have already calculated this length. Okay, and you have calculated this length also. Okay, this length. Then you can calculate the point here using that length, and also you have calculate this length from here to here. Okay, so you can calculate this point also. So you have to calculate x and y point, x and y axis point. So this is in coordinate, no? This is in x and y coordinate like this. Okay. Now we have changed our coordinate. Okay, because we have shift. Okay. I think that shifting may be easy. Okay. I don't know. Okay. But if you can do this without shifting. Okay. So here you have x-axis and uh, here you have the y-axis. Okay, not here actually. So not here. Here after 5 mm, you have the x-axis, and here you have the y-axis. Y-axis is here, and here x-axis you have 5 mm because we have shifted. Okay, so you see this. Okay, so here this is in x-axis and this is 5 shifted. Okay, so what is this value? You can calculate this value, and you can calculate this value, and you can calculate this value. Okay, so give me a 20 minutes around. Okay, I will calculate this point and get you back. Okay, so I think it will be easy. Okay, otherwise if we are going to calculate this by hand, okay, this in our mind, it will make confusion. Okay, so I think it is hard to draw here also, because the lines are not I can't draw a straight line. Okay, so mm, I will use a pen and a paper, and um, I will return. Okay, so meanwhile you can find this point by yourself. Okay, so this is your x-axis, this is your y-axis, and already you have this is 5 mm. Okay, this is 5 mm, and what is this length here to here? It should be 2.4.